Okay, hi guys. Let's talk about Chapter 5 and just do a little bit of an overview on the Chapter 5 on modeling randomness. I have a few slides here that just touch some of the high points. Main topics: probability distributions, what are they and how do you work with them? The distinction between discrete and continuous distributions, the idea of center and spread applied to probability distributions. And then we've got these three specific types of distributions: the Poisson, the binomial, and the normal. There are really many probability models, but these three are very common and useful, and we're going to work with them a lot in the course and in your homework. A couple of this kind of the major ideas or terms from the chapter. A random variable, as opposed to the variables that we talked about in Chapter 1 and Chapter 2, where you just had a variable being some value that would take different values in different situations. Here we're thinking about a random variable being something that takes different numeric values depending on the outcome of a random process. So there's some kind of random process occurring, and as a result of that process, you have some value that varies as a result of the process. That's a random variable. And then a probability distribution describes that random variable. Basically, it's a model for random behavior that specifies what are the specific values a random variable can take. So what are the specific outcomes of this random process? And it has to give you some kind of method for determining what the probability of each of those values is. What can happen, and what are the probabilities of various things happening. So here are a couple of kind of simple examples. The first one, you have the random process of spinning a roulette wheel at a casino. And those of you who are familiar with roulette will know you can bet on a specific outcome, or you can bet on maybe the ball landing in the red slots, or the black slots, or the green slots. Well, if you make a bet on that, if you make a $1 bet on red, there are two possibilities. You either land in one of the 18 red slots on the roulette wheel and you win $1, or you land in one of the 20 slots that are not red and you lose $1. So capital X is your random variable. It takes values 1 or -1. Basically your winnings or your results in this experiment. And the probability that you actually win $1 is 18 out of 38, or about 47.37%. The probability that you lose $1 is about 20, or exactly 20 and 38, about 52.63%. This is a probability distribution because it tells you exactly what values the random variable can take, and it tells you exactly what the probability of each of those is. Notice the characteristic: these probabilities are always going to be between 0 and 1 because they're probabilities, and they're going to add up to 1 because something's got to happen. In this case, you're either going to win $1 or lose $1. Here's another example. A random process is measuring a random U.S. male. So select an adult male at random from the population and check his height. That's a random process, and it has various outcomes. If you think about it, this is quite a bit more complicated. There are really infinitely many possible outcomes, possible heights, and they would correspond to real numbers on an interval, right? You could have all kinds of different heights. So to describe a probability distribution for this, we need to somehow kind of say what can happen and what the probability of each event would be. Y, our capital Y being our random variable, could take any positive real number value. Well, I guess for heights of men, in practical situations, it's probably going to be between about 60 and 80 inches most of the time. But in theory, this could take, a wide range of real numbered values. And then the probability of, say, having this randomly selected male be 6 feet tall, if you mean 6 feet tall to the nearest inch, Well, maybe that means that you'd measure them somewhere between 71.5 and 72.5 inches. In a continuous probability distribution like this, where the value can take any real number on an interval, in theory, the probability that a randomly selected male will be exactly 6 feet tall, 72.00000000000 inches, is in theory 0, right? Because if you can measure accurately enough in one of those decimal places, you're going to differ somewhat from 72.0. So the way we handle that in our model is we think really what 6 feet means is it means a certain range of measurements. If we measure between 71.5 and 72.5, then when we round to the nearest inch, we're going to say 6 feet tall. And we model that as an area under the curve, so that the heights are on this axis, the total area underneath this bell-shaped curve is 1, and the probability of selecting a male that fell in this range would be this shaded area in here, some percentage of the whole. Okay, so X, the example about the roulette wheel, that's a discrete random variable. It can only take 2 values. It's a dichotomous random variable, only 2 values. And the mean of the distribution could be calculated with this general formula that works for any discrete distribution. Here's the formula. It really is pretty simple. It just means add up sum of all of the values. K is typically used for the specific values. In this case, it's just 1 and -1, times the probability of each. So you win $1 47% of the time. You lose $1 52% of the time. If you follow the formula, the mean of that distribution is -0.0526. Can you interpret this result in context? Let's see. Helps to think units. That's really $1 and -$1. So this comes out -0.0526. So really what this means is that in the long run, even though on every trial you either win $1 or lose $1, in the long run, a gambler is going to lose about 5 cents, about a nickel, every time they bet $1 on Reddit in roulette. That's kind of the long-term average result. So here's the picture for the continuous example again. For y is a continuous random variable. It takes infinitely number of values on a continuum, and the probability distribution of U.S. men's height follows a smooth, symmetric bell-shaped pattern called a normal probability distribution. Through many observations, we know that this has a center at 70 inches and a standard deviation of about 3 inches. And if you look at a large number of observations, you get a very symmetric bell-shaped pattern occurring like this. In the homework, you have a lot of situations where you're finding probabilities using one of these standard models, the Poisson, the binomial, or the normal distribution. And I'll give you a separate talk about the fine points of distinguishing which one to use in which situation. That can be the hardest part. But let's talk a little bit about how the calculator works with these. So here's an example. The number of calls received each minute at an office follows a Poisson distribution with mu equal 2.7. So really what that means is that, let's see, if you look at a whole lot of minutes and count up the number of calls that come in each of those minutes, the average is about 2.7 calls per minute. You get about 2.7 calls per minute, okay? And because those are scattered in time, more or less randomly, this is a situation where we might anticipate that a Poisson model would work. The actual random variable is how many calls come in a randomly selected minute. So even though the average is 2.7, the actual observed values of the random variable, we could get 0 calls in the next minute, or 1, or 2, or 3. It's got to be a whole number. That's why this is a discrete random variable. It just takes these specific values, okay? And then the question here is essentially what's the probability that the value in this next minute is going to be 5 calls, okay?